I hope that by playing around with the applet, you were able to come up with some idea about how the graph of f inverse relates to the graph of f. I've drawn a representative one here. This is my graph of f of x. It might be x cubed or x to the fifth. And this is the inverse, cube root of x, or the fifth root of x. And so we see that the graph of f inverse of x is the graph of f of x and it's a reflection, but unlike the examples we saw earlier tonight where we were reflecting around either the x-axis or the y-axis, now we're reflecting around this diagonal line, 45-degree angle line, y equals x. So the graph of f inverse of x is the graph of f of x reflected about the line y equals x. And this will be useful to us, especially next week. We already know what the graph of an exponential function looks like, and for free, using this fact, we'll be able to get what the graph of its inverse function looks like. Now let's try an example here. Suppose we have this function, f of x equals 2 to the x plus 5, and for each of these four expressions, we'd either like to figure out what they equal as a number or say that they're undefined. So when we say f inverse of 9, remember, this is saying that 9 is the output of f of x. So this is saying we're trying to solve f of x equals 9. In other words, solve 2 to the x plus 5 equals 9. Now I've drawn the graph of 2 to the x plus 5 over here. This uses things that we've figured out earlier today. You use the applet to figure out what the graph of 2 to the x looks like, and then you use another applet to figure out that when we put the plus 5 there, that just shifts the graph up and down. So this graph of 2 to the x used to have a horizontal asymptote at y equals 0, but we shifted it up to y equals 5. So if we're saying f of x equals 9, that means we're asking to go up here to 9. Is there going to be an x value where the y value is 9? Yes, there is. Now, can we figure out what that x value is? If we're lucky and we can make a good guess, we can. Otherwise, we need to use logarithms, which is what we're going to start off next week with. But in this case, by good luck, it's a nice integer that we can plug in here for x to make this equal. In fact, 2 to the 2 is 4. 4 plus 5 is 9. So f inverse of 9 is, in fact, 2 here. Now what about part B, f inverse of 3? That's saying go down here to y equals 3. Is there going to be an x value where the y value here is 3? In that case, we see no, because the lowest that the y value ever gets here, well, we have an asymptote at y equals 5. The y value never gets down to 5 or below. So this is undefined. This is saying f inverse of f of 28. Now, we could make this really hard. I could take 2 and raise it to the 28th power. That's some huge, huge, huge number, and then add 5 to it. Well, what's going to happen? I'm going to get some huge, huge, huge y value. But then f inverse says, what was the x value that gave you that y? What was the x value that gave you that y value? And it's supposed to undo the work of f. So if you put 28 into f, and you take that answer and you put it into f inverse, they should undo each other, and the answer should be 28. Similarly here, f inverse of 13, if I were to extend my graph up here a little bit, the x value that gives a y value of 13 is not a nice x value like it was here for 2, but we don't care. Whatever it is, there is an x value here. I find out what that x value is, and then I plug it back into f, and I'm right back to where I started at 13. Because, as we've said, f and f inverse undo the work of each other. So this leads us to some useful properties of inverses. If I take f inverse of f of x, I should get x. And I said earlier we need to be a little bit careful about this. It's got to be an x that I'm legally allowed to put into f in the first place. So this is true for all x that can legally go into f. And as we said at the very start of the night, the things that we're allowed to put into f are called the domain of f. So for all x in the domain of f. We can do the other direction as well. We can take f of f inverse of x. That will also be x, because again, they're supposed to undo each other's work. But now the x has to be something that I can legally put into f inverse. And if we think back, the things that we can put into f inverse are the things that come out of f. So this should be for all x in the range of f. The reason back here that f inverse of 3 was undefined, so if I tried to do f of f inverse of 3, the answer would still be undefined. It wouldn't be 3 here, because in this particular example, 3 was not in the range of f. The range of f was strictly greater than 5. I'm not allowed to put 3 into f inverse because 3 isn't in the range of f. And then the final two useful properties or useful facts, that just another way of saying something that I just said, the range of f, the things that come out of f, are the things that go into f inverse. So that's the domain of f inverse. And then because f inverse's job is to undo the work of f, the things that come out of f inverse were the things that went into f in the first place. And these are useful facts that we're going to come in handy for us in the weeks to come. All right, so this was pretty heavy on the graphical and the just sort of abstract thing. Let's do one final word problem. So let's suppose that y equals f of x is the number of kilometers that Joan can run in x minutes. And just as we did with our linear function at the start of the night, we want to interpret the following quantities: f of 20, f inverse of 20. And the good thing to do with these problems is to try to get the units right. In this case, what is this? 20 minutes or 20 kilometers? We're told that f of x is the number of kilometers she can run in x minutes. So this is 20 minutes, and therefore the output of this is in kilometers. So this is the number of kilometers. Some people like to say kilometers. The number of kilometers Joan can run in 20 minutes. Because that's what the graph of f does. F starts with an input of minutes and gives an output of kilometers. Now, for our last example of the night, f inverse of 20. F inverse goes the other direction. It undoes the work of f. Remember, the range of f is the domain of f inverse. So in this case, the 20 is kilometers. And the answer is going to have to be a number of what? It's going to have to be a number of minutes. So f inverse of 20 is the number of minutes. The number of minutes what? What does this 20 come in? This is 20 kilometers. So it's the number of minutes Joan needs to run 20 kilometers. So getting the units here is crucial. Here it was 20 minutes. Here it's 20 kilometers. So we have a check your understanding exercise for you to do to see if you have understood this sort of word problem. And just to sum up what we've done this week, we looked at linear functions and exponential functions and shifts and stretches and shrinks and reflections of functions. And we're going to use all of that in the future. And we looked at composites and inverses. And we're going to start off next week where we want to use inverse functions of the exponential function. We'll have an equation that has an exponential function in it. We'll want to undo the work of that function. So we'll need an inverse of the exponential function, and those functions are called logarithms. That's what we'll start off with next week. And before that, you should try the last check your understanding of this week. All right, everyone, thanks for watching.